Welcome to the deep dive. If you work in machine learning for robotics, you know the holy grail is getting a world model that can really predict the future. Well enough, anyway, to plan complex stuff like multi-step manipulation. So today, we're tearing into Semantic World Models, or SWM. It's a paper by Jacob Bird and colleagues, and it's a direct challenge, really, to how people usually think about world modeling. It argues pretty strongly that focusing on pixels might be, well, wrong.
Yeah, it's a provocative idea.
Definitely. So our mission today is to get under the hood. Why does SWM say forget pixels? And how does it use these big vision language models, VLMs, to get apparently much better generalization and robustness for planning?
Right. And maybe before we dive deep, it's worth doing that quick summary. The key takeaways for anyone needing the nutshell version.
Good idea. Hit us with it.
Okay, 4 main points. First, the pixel problem. Basically, standard world models spend tons of effort predicting every single future pixel. But this often misses or messes up the semantic details you actually need, like did the gripper really make contact? Pixel-perfect visuals can hide that.
Okay, so noise over signal. What's the SWM fix?
Second, the SWM solution. They just redefine the whole problem. It's not video prediction anymore. It's visual question answering, VQA, but about the future. So instead of making a video, the model answers questions like, given these actions, will the red cue end up on the blue block? Stuff like that.
Interesting. So leveraging language models.
Third, VLM leverage. Exactly. They take a pre-trained VLM palygemma specifically and fine-tune it. This means SWM inherits all that powerful generalization from the VLM, which also sets up a nice comparison against other big models like AVD, that's the action conditioned video diffusion model, a key panel-based baseline, and also offline RL methods like IDQL.
Got it. And the payoff.
Finally, the impact. The results are pretty striking. SWM Plus planning dramatically boosted success rates on tough robotics benchmarks, LangTable, OGBench. It strongly suggests this semantic prediction approach is, well, more effective and efficient for planning than trying to predict pixels.
Okay, that summary really sets the stage. Let's unpack that first point. The failure of pixels. Why are they so problematic for robot control? Seems intuitive to predict what you see.
Well, historically, that was the intuition. Train a model, see the current state, get some actions, predict the next frame, and the measure of success was, how real does the generated video look?
Visual fidelity.
Exactly. And models got really good at making plausible-looking videos.
But plausible isn't useful, is it? Especially for manipulation. Tiny details matter so much. Like, you could have a great-looking video prediction.
Right.
Where the gripper looks like it touches the block, but maybe it's off by a pixel or two on contact, or the angle is slightly wrong.
And that tiny error, that high-frequency noise, maybe a weird shadow, a texture, shimmer, it gets fed into your planner.
Yeah, which means the planner gets garbage input, essentially.
Precisely. It introduces huge variance. The SWM idea, the core hypothesis is, what if we just ignore all that visual noise? Focus only on the low variance, high signal semantic stuff. Questions like, did the arm get closer? Or was the blue thing picked up? They argue that that information is enough and way more robust for making decisions.
So no more asking for the entire visual future, just specific task-relevant questions, yes-no answers, or maybe short text. That's the VQA shift you mentioned.
That's the shift. You're not predicting this high-dimensional observation space anymore. You're predicting probabilities over text answers, conditioned on the current image and the action sequence you're thinking about trying.
Okay, conceptually that makes sense, especially with how good VLMs are now. But technically, how is SWM different from just a standard VLM? Or even those video world models?
Good question. So standard VLMs, they look at a static image, right? What color the block, that kind of thing. Video world models, they take actions, predict future pixels. SWM slots in between. It takes the current view plus the proposed actions, and it outputs a language answer about the future state resulting from those actions. It's action condition VQA.
Okay.
And they make an interesting comparison to VLA's vision language action models. VLAs usually take instructions, see the world, and output actions.
Right. They generate the robot's behavior.
SWM is like an inverted VLA, as they put it. It takes the actions in and predicts the outcome out in language. And this structure is apparently key. It lets SWM hold onto the VLM's pre-trained knowledge about prediction, even when conditioned on these new action inputs.
Okay, let's get into the weeds a bit. The architecture. How did they actually teach a language model about physics? I mean, how do you feed a continuous robot arm movement into a model built for words?
Right, the technical nuts and bolts. They start with the palygemma 3B checkpoint. That's the Gemma large language model combined with a SIGLIP image encoder. Standard VLM stuff.
Okay.
The magic for handling actions is this new trainable projection matrix, panel others.
So Powner is the bridge.
That's the bridge. Your action sequence is just a vector of numbers, right? Joint angles, maybe end effector poses. It's continuous. Panel Hell takes this vector from its original space, math.bbr and projects it into the same high-dimensional latent space the LLM uses for text tokens, ZLLM.
So the action becomes like a special kind of token.
Effectively, yeah. It gets treated as this non-textual prompt or condition, slotted right in with the embeddings from the image in the question text. This lets the transformer architecture, which is great at sequences and relationships, figure out the effect of the action over time, given the visual context in the question asked. Then it's just standard supervised fine-tuning. Cross-entropy loss to predict the right answer, strings and ASPR for the question cast judo.
Wow. So the model is learning environment dynamics, friction, contact, all that complex stuff implicitly, just within the language model's latent space. No pixel rendering needed at all.
Exactly, which of course requires specific training data. That's where SQA comes in.
Right, the state action question answer data set.
Yeah, an SQA tuple is just current image, the action sequence, the question about the future, QS2SJ, and the ground truth answer, SJ.
And how do they get those answers? That seems like the hard part.
It would be, except they leverage the simulator. This is important. They use privileged information. They query the simulator's internal state exact object positions, bounding boxes, orientations, stuff you wouldn't have in the real world easily. This lets them programmatically generate tons of varied questions and, critically, the correct answers for different future time steps. Automatically, it sidesteps a massive labeling effort.
Okay, makes sense for training. So now we have this SWM model. It sees an image, considers an action sequence, and spits out a probability for, say, yes, the block was stacked. But robots need control signals, not probabilities over text. How do you get from that to actual movement?
Planning.
Right.
Exactly, planning.
Yeah.
They need a way to turn that text likelihood into a reward signal. That's the scalar value function, VT-toller. V-times takes the current state dollars and a proposed action sequence, $. It basically looks at how likely SWM thinks it is that you'll get the desired answer, $, for a set of relevant questions. These questions can be weighted, depending on what's important for the task. The planner then just tries to find the action sequence and maximizes this value function, $.
Maximize the probability of the desired semantic outcome.
Precisely.
And you mentioned they did something clever with rewarding early success. That sounds important for avoiding getting stuck halfway through a long task.
Yeah, really crucial. They call it sub-chunking. Instead of just checking the final outcome after the whole action sequence AR, they break it down. They check the outcome after smaller chunks of action, say aeon and dollars and so on. They query SWM at each of these intermediate points. By optimizing the value function over these subchunks, the system gets rewarded for making steady progress towards intermediate goals. It helps prevent those situations where one small error early on ruins the whole rest of the plan.
Smart. Okay, so what planning algorithms did they actually use with this value function?
They tried two main approaches. For the simpler tasks, things like reaching for a block or separating two blocks, they use sampling-based planning. Specifically MPPI, Model Predictive Path Integral Control. It's pretty standard. Maintain a distribution of possible action sequences, sample from it, query SWM and score them using $, and then shift the distribution towards the better actions. Repeat.
And the results for MPPI on simple tasks were good.
Near perfect, actually. Like 100% success on reaching and separating according to Table 2.
But there's always a but.
The but is compute time. PalaGemma 3B is a big model. Running thousands of forward passes through it for every planning step like MPPI needs gets really slow. Too slow for complex tasks on typical hardware.
Right, so that forced them towards a different approach for the harder stuff.
Exactly. For the more complex LangTable and OGBench tasks, they switched to gradient-based planning. Here, you typically start with an initial guess for the action sequence, often from a simple base policy like a diffusion policy trained on demonstrations. Then, instead of sampling, you directly compute the gradient of the SWM value function JTA with respect to the action tree and use gradient ascent to optimize the action sequence.
Gradient ascent on the actions to maximize the semantic value. And this must be where that efficiency comparison comes in. For our audience, deep in the weeds of ML infra, this is huge.
Oh, yeah. The difference is stark. Gradient-based SWM is taking about 1.56 seconds per action chunk to plan.
Okay, pretty fast.
Compare that to the pixel-based baseline, AVD. Using its own planning approach, it needed 676 seconds, over 11 minutes.
Wow. What's the architectural reason for that massive speedup, like over 400x faster?
It's where the gradient computation happens. For AVD, to get a gradient for planning, it has to backpropagate through the entire, very complex video diffusion model. Generating those pixels and getting gradients through that is incredibly slow. SWM, though, only needs to backpropagate through the PalaGemma model to get the gradient of the text likelihood with respect to the action input. That forward and backward pass through the VLM is just much, much faster than doing it through a pixel diffusion model.
That really highlights the practical benefit of the semantic approach. Faster planning cycles mean potentially more reactive robots.
Absolutely. And this setup also handles longer sequences naturally.
How so? For multi-step tasks.
Yeah. You just define your task as a sequence of subgoals. $, G2, Yoto. Each subgoal corresponds to a question SWM can answer, like, is block A on block B? You use SWM planning to achieve G$ and NAR. Then, crucially, because the SAQA training data included 0 horizon examples, questions about the current state, you can use SWM to verify if G$ is actually complete before you even start planning for G$2. It provides built-in progress tracking.
Very neat. Okay, let's talk results then. The benchmarks. LangTable for combinatorial stuff and OGBench for dexterous manipulation. How much better did SWM actually do compared to the baselines?
The improvements were pretty significant. Let's take LangTable. The base diffusion policy they started with only got about 14.4% success on average.
Okay, not great.
But after refining those actions using gradient-based SWM planning, the success rate jumped to 81.6%.
That's a huge leap. What about OGBench?
Similar story. Base policy was around 45.3% success. SWM refinement pushed that up to 76.0%. And importantly, SWM consistently beat the other main baselines, the offline RL method IDQL, and the pixel-based world model AVD across basically all the tasks they tested.
So, strong evidence that the semantic approach works better for control in these settings. Now, a big promise of using VLMs is generalization. Did SWM deliver on that when faced with stuff it hadn't seen in training, out of distribution scenarios?
Yes, and this is arguably one of the most compelling parts of the paper. They tested O generalization in 2 key ways. First, semantic compositional generalization. In LangTable, they introduced new combinations of block colors and shapes that weren't in the training set. SWM handled these novel combinations much better than the base policy, showing about a 20% performance boost over it.
So it understood the concepts, not just memorized configurations.
Seems like it. Second, they tested scene robustness in OGBench. They just changed the background color as a simple visual change. This completely tanked the performance of the pixel-based AVD model. It got confused by the visual shift.
Ugh, classic pixel model fragility.
Right. But SWM, because it's focused on the semantics, largely ignored the background change and maintained its high performance, again showing a clear advantage over the base policy that AVD struggled with. It really points to the VLM's underlying robustness being leveraged.
That's very convincing. What about data? Did they need perfectly curated expert data for all this?
Interestingly, no. They actually found something quite counterintuitive. Their future question answering accuracy improved when they mixed suboptimal data trajectories collected using just a random policy into the training set along with the expert data.
Really? Adding random data helped?
Yeah. It sounds weird for policy learning, but for training the world model part, seeing failure cases and noisier trajectories seemed to help SWM better understand the boundaries, like when certain actions lead to success versus failure.
That's a potentially huge implication for real-world use, where getting purely expert data is hard and expensive. Mixing in cheaper, messier data could actually be beneficial.
Potentially, yes.
One last check before we wrap the findings. Interpretability. How do we know SWM isn't just finding some clever latent shortcut that happens to work, rather than truly reasoning semantically?
That's always a fair question with big models. They looked into this using attention maps. They visualized where the model was looking in the image when processing the language question. So if the question was about the red moon touching the blue block,
Big attention should be on those objects.
Exactly. And it was. The attention maps clearly showed the model focusing its visual processing on the task-relevant objects mentioned in the query, ignoring irrelevant parts of the scene. They even showed some zero-shot attention capability, asking about 3 objects when it was only trained on 1 or 2, and the attention still correctly highlighted all 3. It strongly suggests it's using the VLM semantic grounding.
Okay, so synthesizing all this, SWM flips the script. It replaces noisy, computationally heavy pixel prediction with efficient, high-level semantic VQA about the future. And this leads to robotic policies that are more robust, generalize better, and can be planned orders of magnitude faster.
That's the core takeaway. But it's not perfect, of course. There are limitations.
Right, let's touch on those. What are the current hurdles?
Well, the computational cost is still a factor. Even though gradient-based planning is much faster than AVD's approach, PaLGemma 3B is still a large model. This means that the simpler, perhaps more robust, sampling-based MPPI planning is still too slow for real-time use on current single GPUs. So for now, the fast gradient-based approach relies on having a reasonably good base policy to initialize from.
Okay, so compute is one. What else?
The other big one is data requirements. Generating that SIQA dataset currently needs that privileged information from the simulator, the ground truth object states.
Which you don't have easily in the real world.
Exactly. So bridging that sim-to-real gap for data generation is a major challenge for deploying SWM beyond simulation right now.
That naturally leads to future work. What are the promising paths forward?
Two main directions seem obvious. First, tackle the VLM size. Can we get similar SWM performance using smaller, more efficient VLMs? Maybe models like fast VLM or small VLM. If you could get the inference fast enough with a smaller model, maybe sampling-based planning like MPPI becomes feasible again, which could remove the dependence on having that initial base policy.
Makes sense. Shrink the model. What's the other path?
Address the data problem. Can we get rid of the need for the simulator's ground truth? Maybe you could use a powerful foundational VLM itself to automatically generate the question-answer pairs from real-world robot interaction data. Use one VLM to label data for training another, smaller SWM. That's a potential route to real-world data integration.
Interesting. Using VLMs to bootstrap the training data for other VLMs.
Could be a way forward.
Okay, this has been a fascinating look at SWM. It really does challenge some core assumptions in robotic learning. Which brings us to our final thought for you, the listener, to chew on. If SWM is right, if predicting the future state of the world can be effectively boiled down to just answering a structured semantic question about the outcome, did X happen? Yes or no, how fundamentally does that change how we should think about designing reward functions or breaking down complex goals for robots in the future? Does everything just become a sequence of verifiable semantic questions?